Welcome back. This is week 2, chapters 3 and 4 in our astronomy course. Chapter 3 begins with orbits and gravity. So every 90 minutes, a spacecraft in low Earth orbit, such as the International Space Station or the ISS, will make one orbit traveling at 17,500 miles an hour. That can cross from Los Angeles to New York in just a matter of minutes. We're taking a look at the ancients, that studied astronomy. Here we have Tycho Brahe and Johannes Kepler. Now, Tycho was an astronomer, whereas Johannes Kepler was really more of a mathematician, and the two worked well together. Kepler worked for Brahe, or we just call him Tycho. So what Tycho did was he made very precise measurements of objects in the sky, stars and planets and Mars and various things. We want to be able to draw out an ellipse because this is the shape of the orbits of the planets, not circle. And this gets into Kepler's laws of planetary orbits. So Tycho Brahe made 40 years worth of measurements and then died a terrible, terrible death. He was eating dinner with the King of Denmark. He was the world Danish astronomer. And the rule was you did not get up from the table until the king had gotten up from the table, where the king was a large man who could withhold his ale and beer and whatnot. And Tycho had to go use the facilities, but he could not get up, especially with him being as important as he was. He could not get up from the king's table. Excuse me. And what ended up happening was his bladder exploded and he died a couple days later. So Kepler took over the data, and before Kepler got hold of the data, we still believed that the orbits of the planets were circles. Now we don't, and the sun is a little bit off center. So to draw an ellipse, you can pick two thumbtacks into a corkboard, put a piece of string between them, and then draw out the ellipse. The further across the two thumbtacks are, the longer or skinnier the ellipse is going to be, and the more elliptical it will become. Kepler's second law is the law of equal areas. In a 3-month span of time, a planet going from point 1 to point 2 here will sweep out an equal area with the sun as a point from 3 to 4 over here on the other side of the sun. So think of like a pizza box. You're eating some pizza, you got a big slice of pizza here, but then you have a narrow, long slice of pizza. Those two pieces of pizza will be the same amount of pizza. So what that means is that when a planet is near the sun, it has to clear out more of the orbit than when it does when it's farther away. It goes slower when it's farther away and faster when it's closer. And then here comes along Sir Isaac Newton, the father of modern physics. Newton's third law of physics. Here we have the retired U.S. Space Shuttle. This was Discovery launching. Powered by 3 fuel engines burning liquid oxygen, liquid hydrogen, and 2 solid fuel boosters. Newton's third law says an object in motion will remain in motion, an object at rest will remain at rest unless acted upon by an outside force. Equal and opposite forces. His law of conservation of angular momentum says that when a spinning figure skater, and if you watch the Olympics, you'll see this, they bring in their arms and their skates and they spin very rapidly. This is conservation of angular momentum. While you're in space, here in the cupola module of the International Space Station, where the astronauts like to hang out and see the views of the Earth, they are actually free-falling throughout the space station, but they all free fall at the same speed. We can simulate this on the Earth by taking a special modified 747, they call it the Vomit Comet, and it makes these parabolic arcs across the sky. And as it falls, you fall along with it and you free float. Now, orbits in the solar system, most of the planets are almost circular, the exception being Mercury and Pluto. Pluto's not a planet. Comets tend to make very highly elliptical orbits in the solar system. So if you were to fire a bullet, of course it would hit the ground at some point. If you fire that bullet fast enough, it would eventually go into orbit around the Earth, and that speed is 17,500 miles an hour. We have thousands of satellites in Earth orbit, meaning them are dead. And NASA tracks all of this because we don't want space debris, burn off rocket parts or broken satellites that are dead, to crash into anything that's out there, like the Hubble Space Telescope or the International Space Station. I have a colleague of mine at a former university I worked for, Drury University, who studies space debris for NASA. And so we have the computing power to track the motions of anything but the size of a marble. We actually did an experiment with the space shuttle once. We launched several objects of different sizes, and we could actually track the size of a marble throughout space. Now, mathematicians who discovered a planet, John Couch Adams and Leverrier, discovered Neptune using mathematics. So they knew that the planet Uranus is being tugged and pulled on, and it had to be by something other planet outside of its orbit. Now we go on to chapter 4, the Earth, Moon, and Sky. On the Earth, we use latitude and longitude to describe a position of something. Latitude is like a ladder sounds. It's up and down. Whereas longitude is a long ways around the globe. And so we start at the prime meridian and go from there. Start at the equator, go from there. Here in Greenwich, England, at the Royal Observatory, we have agreed upon the 0 point of longitude goes right through where longitude, goes through, just outside of London. This is a picture of Foucault's pendulum at a science museum. As the Earth turns, the plane of oscillation under this pendulum shifts. The pendulum goes in a straight line, but we go in a circle underneath it as we orbit and rotate. And so these little pegs get knocked down every so many minutes. Seasons. Why do we have seasons? One misconception is that we are closer to the sun in the summer and farther in the winter, and that is simply not true. We are actually closer to the sun in the wintertime, 91 million miles away or so, than we are in the summertime, 94 million miles away. It's actually the tilt of the Earth that causes the seasons. So we are tilted towards the sun in the summertime in the northern hemisphere. We're tilted away from the sun in the wintertime in the northern hemisphere, and then Australia heats up. Right now, Australia in mid-January is heating up to over 120 degrees in places. So it has to do with the angle of the sun's rays. More direct in the summertime, less direct and diffuse in the wintertime for the northern hemisphere. So here we see the tilt of the Earth on June 21st, the first day of summer. We see that the northern hemisphere is tilted more towards the sun, and that gives us the most intense radiation, but it still takes another 4 to 6 weeks for the land to heat up. That's why June 21st is not the hottest day of summer. It's more like middle of August. And then hurricane seasons tend to peak more along in September, late September, because the water takes about 8 to 12 weeks longer to heat up. So we have the international date line where we change the dates in the Earth, and we can see how it straddles Russia and Alaska right here in the Bering Strait to the Aleutian Islands. And so every New Year's Eve here in New Zealand, Papua New Guinea, they're the first ones to bring in the new year. Here is Stonehenge, which was probably an ancient sun-worshipping object to keep track of the motions of the sun and the moon. El Cacaro, this Mayan observatory in the Yucatan of Mexico, dates from the year 1000. Phases of the moon. You know, we go through the phases of the moon over the course of about 30 days. And so we go from new moon, where the moon is between the sun and the earth, and we don't really see a moon. And then we start going through the phases as it goes around the earth, and more of it gets lit up by the sun. We start with a waxing crescent, and then a week into we get the first quarter. 2 weeks into it, it's on the other side of the earth, and we get a full moon. 3 weeks into it, we get third quarter moon. So a solar eclipse can only happen at new moon. A lunar eclipse, when the moon goes through the Earth's shadow, can only happen at full moon. But it doesn't happen at every new and every full moon, because the tilt of the moon is about 5 degrees in its orbit, so it's not always right in a line. And the size, angular size of the moon and the sun are both about 1/2 of a degree. You could cover up the moon with your thumb, or the sun with your thumb. Close one eye and try it one day. Close your eye and you put your thumb up over the sun, or at night over the moon. Now the moon is actually pulling on the earth, and this causes tides. Depending on what phase the moon is and what's its position on the earth, we get spring and neap tides. So ideally, you get more water flowing towards the moon. Here we have the Bay of Fundy in Canada, which shows extremes of high and low tides in its position physically on the planet. So the tides are caused by different alignments of the sun and the moon. Spring tides, the sun and moon's pull reinforce each other. And in neap tides, the sun and the moon pull at right angles to each other, and the tides are lower than usual, and we get a high and low tide every 12 hours. George Darwin, best known for studying the Earth's spin in relation to its angular momentum. Here we have a solar eclipse where the moon is in a new phase. We had a total solar eclipse on August 21st of 2017. Maybe many of you saw the majority of that. And so in this case, the moon casts a very narrow shadow onto the Earth's orbit, but everybody else wasn't under that very narrow shadow where totality exists, still sees part of the eclipse outside of this shadow. If you were in a totality, which I was in Fenton, Missouri, about 3 hours north of me in Springfield, Missouri, I got to see the corona, the outer hot layer of the sun, for 2.5 minutes, and that was wonderful to see. So a lunar eclipse is when the Earth gets in the way of the sun and the moon travels through the Earth's shadow. And it turns red, and anybody on the dark side of the Earth, half the population, can see the lunar eclipse. So lunar eclipses are far more common than solar eclipses are. And they seem to be a reddish hue, and that is because the sun's light shines through the atmosphere of the Earth and casts a sunset onto the moon. And we can measure how polluted the Earth's atmosphere is as a whole by how red that light is. If it's very red, very polluted. And then here was the path of the totality of the eclipse in 2017. I was stationed up here in Missouri, and you guys down here in Georgia saw about 90% of the eclipse.